We have two talks today. Our first speaker is Zhang, who is currently a postdoctoral research associate at the Department of Aerospace and Mechanical Engineering at the University of Notre. He obtained his PhD from Baylor University, and after that, he went to Georgia Institute of Technology as a postdoctoral fellow. His research focuses on liquid fuel atomization, droplet dynamics, shock waves, aerodynamics, reacting flows, advanced multi-phase forming for paper making, and also machine learning methods for fluid mechanics. Welcome, Dr. Zhang. So you may want to start your presentation.
Okay, thank you for introduction, Songren. Good afternoon, everyone. I am Zhang from the University of Notre Dame. Today, I'm going to talk about nonlinear mode decomposition for the unsteady flows over NACA 4412 airfoil near stall conditions where physics-assimilated neural network. This presentation consists of introduction, results, conclusions, my recent and future work. Now let's move to the introduction session. The airfoil, the airfoil is a key component for the fighter crafts, F-22 and F-35, B-2 bomber, Boeing airplanes, gas and wind turbines. The study of the airflows around the airfoil plays a crucial role in designing those components. The cross sections of the airfoil in the airplane and the turbine blade are just the two-dimensional airfoils. The angle of attack is an important concept in airfoil designs. It is defined as the angle between the airfoil chord line and the vector along the relative wind flow directions. He says there are also two important parameters, namely the lift and drag coefficients, which are defined as the lift and drag over 1/2 rho u squared times the cross-sectional area of the airfoil, with rho and u the free stream density and velocity respectively. With the increase in the angle of attack, the lift will increases. And when it is close to the peak value, airfoil stall happens, which induces a sharp increase in the drag and decrease in the lift. It had an important impact on the aerodynamic performance and the flight maneuverability. So the goal of the present study is to develop a physics-assimilated convolutional autoencoder neural network to carry out nonlinear mode decomposition of the unsteady flow field around the NACA 4412 airfoil near stall conditions. Let's start with the result session. First, let's take a closer look at how to perform dynamic mode decomposition DMD analysis. Given a sequence of spatial temporal snapshots X, the time-shifted snapshots X prime can be obtained. X prime is related to X by a best fit operator A. Now the DMD analysis can be taken as a combination of proper orthogonal decomposition POD and the Fourier transform. So the resulted spatial DMD modes is closely related with a temporal frequency with a growth or decay rate. Nevertheless, in practice, it is intractable to analyze the for matrix A due to its super large dimension. So we resort to analyzing the reduced matrix A tilde, which is the R by R projection of the for matrix A onto POD modes. So first, takes a singular value decomposition of X. Second, obtain the reduced matrix A tilde. Then compute the identity decomposition of A tilde. Finally, the DMD modes are given by phi. The temporal dynamics can be reconstructed by DMD analysis, and the future state can be predicted. If an eigenvalue is distributed on the unit circle, the DMD modes will be stable. Otherwise, if the eigenvalues are inside or outside the unit circle, the modes will converge or diverge respectively. Moretta et al. Have performed nonlinear mode decomposition of the flow field using mode decomposing convolutional neural network autoencoder. Nevertheless, the decomposed modes cannot be physically interpreted. Recently, Hack et al. Combined DMD and autoencoder to obtain the foreground and background of sequential temporal images. The DMD modes are distinguished into the foreground modes and background mode resulting to the DMD mode splitter. Then those foreground modes and background modes are used to obtain the foreground and background of the images through the decoder part of the well-trained autoencoder. Now let's take a closer look at the architecture of the physics-assimilated convolutional autoencoder neural network, namely AENet, for the current study. So firstly, the autoencoder is trained well using the airfoil flow field data. Then the snapshots are fed through the encoder part of the well-trained autoencoder to obtain the latent vectors. After that, the time-shifted latent vectors are obtained. Thirdly, those latent vectors are used for DMD analysis. Then the high and low frequency DMD modes are obtained, covering different frequency ranges by the DMD mode splitter. Those high and low frequency modes are fed into the decoder part of the well-trained autoencoder to obtain the nonlinear modes covering different frequency ranges. Hence, the AENet can be seen as a combination of autoencoder and DMD. I have performed the DMD analysis of the flows over the airfoil near store conditions. First, taking the transverse velocity field as an example. As shown in the left figure, most of the discrete eigenvalues are situated on the unit circle, indicating most of the DMD modes are stable modes. And for the transformed eigenvalues omega, the real and imaginary parts represent the growth rate and the frequency of the DMD modes. As is seen in the right panel of the figure, the DMD modes are closely related with the frequency of the DMD modes. And at higher DMD frequencies, the most of the DMD modes are situated close to the airfoil surface. The similar conclusion can be drawn for the DMD analysis of the streamwise velocity fields. I have examined the representation of the reconstruction ability of the—
Sorry, I have a question.
Uh-huh.
If you were to plot the POD modes here, how would they look different?
Oh, you mean the POD modes?
Yeah.
POD modes, generally actually I didn't show it in this slide. In my previous paper published in Computed and Fluids, I show it. Generally, it for the spatial modes, it looks similar. But if you check the details, there are some small differences. But the difference is for POD mode, you cannot find the dominant frequencies, but you can rank the energies of for each mode.
Okay. So is the first mode is different? That's what you're saying?
Oh, you mean between the POD and DMD, right?
Yeah.
Between POD and DMD, the first mode is also— oh, for POD you rank the mode by the mode energy.
Yes.
But for if you check the dominant mode, it look different from what I show here for the DMD mode. But for DMD modes, it actually classified by the growth rate and the oscillating frequency. So actually, it looks a little bit different.
So here you rank them in terms of the complex eigenvalues, right?
Yeah. Exactly.
But they look to me similar.
Yeah, the spatial mode looks similar, but the POD cannot give you the frequency information and the growth rate information.
I see. Okay, thank you.
only this difference. And because the pure DMD, you can take it as a combination of Fourier transform and POD. So it's like an upgrade of POD.
Yeah, sure.
Okay. Thank you for a good question. So any other question? Okay. So I examined the reconstruction ability of the DMD modes for the streamwise and the transverse velocity field. The coherent structures in the shear layer and the weight can be well recovered by the DMD analysis. Nevertheless, the finer skills cannot be well resolved. And furthermore, the reconstructed flow fields from DMD analysis are much noisier than their ground truth counterparts. In contrast, the convolutional autoencoder model can well recover the velocity fields. As we see, both the larger coherent structures in the shear layer and the wick, and also the finer spatial skills can well represent it. I also compared the CE model results with the autoencoder model combined with dynamic mode decomposition analysis. As seen, due to the linear nature of the DMD analysis, the AEDMD model cannot recover the flow fields as well as the CE model. Even increasing the DMD modes from 800 to 900, the velocity fields the reconstruction of the velocity field cannot be improved too much. I have also tested the effect of the number of DMD modes used for the nonlinear mode reconstruction. As seen, when using the 100 DMD mode, the temporal evolution of the nonlinear modes can be well represented. This point can be even better examined by examining the discrete eigenvalues, the transformed eigenvalues, and the energy spectrum. With increasing the number of DMD modes used for the reconstruction, the number of the damped DMD modes diminishes significantly. Furthermore, the growth rates of the DMD modes gradually approach zero with increasing the number of modes. The decay of the energy spectrum gradually disappears as the number of DMD modes increases. I have examined the influence of the frequency ranges used for the reconstruction of the nonlinear modes. As seen, when the frequency is in the interval of 100 to 200 Hz, the nonlinear modes can be well recovered, while the others, you can see the nonlinear modes will be exaggerated as time elapsed. Now I have also tested whether the decomposed nonlinear modes is a linear superposition of the modes in the subranges of the checked range. As seen, the addition of the two linear modes to linear modes in the subranges is very different from the decomposed nonlinear modes by using the AENet. Since the nonlinear modes are obtained by the convolutional autoencoder, which possess nonlinearity due to the activation functions, and they prevails over simply a linear combination of the decomposed modes. The influence of the number of latent variables in each latent vector in the latent space of the DMD analysis are also examined to check the representation ability of the AENet. As is seen, for both cases, most of the modes are stable modes. When the number of latent AE variables are increased to 2048, the proportion of the stable modes is higher than the case of using 512 latent AE modes. I also checked, compared the above two cases at different frequency ranges. As you see, when using 2048 latent AE modes, the nonlinear modes can be well recovered. Nevertheless, when using a less number of latent AE modes, the nonlinear modes will be exaggerated too much as time elapses. This is due to when using 2048 modes, we can avoid the loss of information and captures a very good compact representation of the underlying flow dynamics. Now let's take a closer look at the nonlinear modes of the transverse velocity fields. The nonlinear modes look similar to the DMD modes. Nevertheless, the nonlinear modes evolve with time, which is different from the DMD modes, which are purely spatial modes bound with a frequency. The shaded coherent structures for the nonlinear modes can be observed when the frequency is higher than 100 Hz. And with increase in the frequency, more coherent shaded structures can be observed. Similar conclusions can be observed for the streamwise nonlinear modes of the streamwise velocity field. And it is worth noting that the decomposed nonlinear modes for the streamwise velocity field look very different from its counterpart in the DMD analysis. In this slide, I will show the energy spectrum of the nonlinear mode, which are obtained by ranking the Frobenius norm of the nonlinear mode. Each mode number corresponding a frequency range, namely the 100 Hz of the DMD modes. As is seen, for both transverse and streamwise velocity fields, the first four nonlinear modes are dominant. So to sum up, I have applied the physics-assimilated convolutional autoencoder for nonlinear mode decomposition. The physics is incorporated into the neural network by assimilating DMD frequencies into latent modes of AE. DMD analyses are performed. More DMD modes are required to better reconstruct nonlinear modes. The dominant nonlinear modes are obtained by analyzing the energy spectrum of the nonlinear mode. Now I want to briefly show my recent work. Now I'm developing the differentiable hybrid neural solver for cavitating flows. So I will combine develop the implement the numerical method in the JAX framework, and then combine it with the neural network to accelerate the computation. And my next work is concerning the pure data-driven model and hybrid neural solver dealing with Boltzmann transport equations for the submicron heat transfer of thin field effect transistors. Now let's take a look at my future work plan. I will generalize the physics-assimilated neural network's plans to assimilate various physical laws into the model. Furthermore, I will develop Banach neural operator for operator learning. I will develop mathematics-approved graph-invigorated neural network MagicNet to handle submicron heat transfer problems. We will, for example, simulate a three-dimensional single transistor, and then you can imagine you have an array of transistors in a 2D graph. Each transistor simulation is performed by an unstructured mesh. This is the graph. And then the array of the transistors is another graph. So I believe an innovative and revolutionizing computational neural network and also numerical simulation framework will be done by this kind of design. Thank you for your attention. I'm ready for take all of your questions.
Hello.
Hi.
Dr. Bo, my name is Vivek and I'm a PhD student working with Professor George Kaniadakis. Great talk, Dr. Bo. I had a question for you. So the input to your model, how many time steps are you feeding as input to your models and how many time steps ahead are you predicting? I didn't get that part.
Oh, you mean for this part?
Yes. For the flow field, how many history points are you considering? And how many time steps ahead are you predicting into the future?
And okay, actually I have two works. This work focused on the nonlinear mode decomposition. My another work is focused on the prediction of the flow field. For this one, I didn't use the test dataset. It's both in the training and validation dataset. So 1,000 snapshots are used to obtain the latent space.
Okay. Okay, so this is like an analysis of dynamical mode decomposition in a lower dimensional manifold and projecting it back into the space where you are not learning the dynamics.
Yeah, very good question. Yeah, exactly.
Yes.
It was not for prediction, actually it's for the
evaluation. Right. I understand. Thank you, Dr. Bo. And yep, that's all, Dr. Bo. Thank you.
Thank you.
Bo, what's the Mach number here and the Reynolds number?
You can take a table. Mach number is around 0.2, very low, and the Reynolds number is 1.6 times to the 10 to the 6, 1.5 times 10 to the 6, and the Mach number I didn't put here. It's around 0.2, very low.
I see. So you have a turbulence model, right? You run this with a turbulence model.
Oh, actually, I use I use the open form to obtain the data. I use a compressible flow solver.
Yeah, but they have a turbulence model. That's a Reynolds number.
Yes, I use turbulence models.
Dr. Bo, just a follow-up question. What was the airfoil geometries, or how many different airfoil geometries do you consider, or is it just one geometry?
Okay, I only consider the NACA 4412 airfoil, but yes, you can consider a wide range of geometries. And my next work will focus on, for example, using different physical scenarios. For example, no matter a cylinder or mixing layers or relative instabilities. Or
right.
Yes, I want to
extend it. Yeah, thank you. So right now, for a different geometry, you need to do the training procedure again from scratch, right? Just
for each one, if I use this, if I assimilate the physics following the autoencoder model.
Yes, that is true. Yeah.
But I want to test and try whether I can, for example, instead of using autoencoder, using the other neural networks, the other physical laws, and try to interweave them to get some interesting physics prediction.
Thank you, Dr. Bo, for your answers. Thank you.
Thank you for
somebody suggested to me to use the DMD modes as an input to the trunk net of the depot net that we have. I don't know if anybody has done it, but maybe it sounds a good idea because we use the POD modes in the trunk and we got good results. I think some data, one of our Crunch members, but using the DMD modes may be a good idea actually in the trunk. Nobody has done it so far. Actually, the people from Air Force suggested that we try that.
Yeah, very cool stuff. And also I plan to develop the so-called Banach neural operator to study the deep learning in the infinite dimensional space. Because I know
all the neural operators are in Banach spaces because they're
I know there are Fourier neural operators. They are developing the neural operator based on the Fourier transform. But if I want to study the DMD, I think it will be another research lab. DMD is actually a combination of POD and Fourier transform. So it can.
My only worry is that you need a lot of modes, 2048 modes to just reconstruct a flow that looks pretty smooth to me.
You mean how many modes I used? Right?
Yeah.
For this one, I used 900. For some, depends on the kit. Because the more modes I used, the more the nonlinear modes will be reconstructed much better. But it also depends on for example, the number of modes you used for DMD analysis first. For example, if you use 900 DMD modes, 500 flow fields for DMD analysis, but you all only use 200 modes for nonlinear mode decomposition, and then at time elapses, you will see the modes like damp out. So I usually use as many more modes as possible.
Yeah. Yeah. Thank you very much.
Thank you for a good suggestion. I'm quite.
Is there any other questions from the audience? No? All right, thank you, Dr. Zhang, for your presentation. And yeah, and now we are moving to our second talk. So could you please stop sharing your screen?
So thank you.
No problem. So, Katayoun, are you there?
Yeah, I'm here.
Oh, hello.
Hello.
Yeah, let me introduce you to the audience. So our second speaker is Katayoun, who recently completed her PhD in industry engineering from Ferdowsi University. Her doctoral research focused on developing novel structures for pins, with a particular emphasis on applying pins to various engineering problems such as thermoelasticity, diffusion, and reliability analysis of complex systems. Welcome. You may want to start the presentation.
Can you see my screen? Okay. Thank you. I want to start by expressing my appreciation for the opportunity to join this distinguished academic seminar. It is a true honor to be part of this gathering of brilliant minds. I'd like to extend a special thank you to Professor Karnadakis for his generous invitation. Your contributions to the field of PIN have been a constant source of inspiration for me. And I feel incredibly privileged to be presenting at the Crunch seminar. Let me introduce myself. I'm Katayoun Eshkofti, a recent PhD graduate in industrial engineering. My research revolves around applying pins to engineering problems, and I've had the privilege of delving into various aspects of this field during my doctoral journey. As you may be aware, we face certain internet limitations in my country. But I have made every effort to establish a stable internet connection. I hope that everything processes smoothly and without any interruption. Today, I will be discussing a modified version of PIN known as the gradient enhanced gPINN or PIN, and its application is analyzing generalized coupled non-Fickian non-Fourierian diffusion-thermoelasticity. This novel approach has shown promising results in function approximation and single PDE problems in previous studies, and I'm excited to show you how it can be extended to tackle a system of coupled PDE. I would also like to acknowledge my supervisor, Professor Sayed Mahmoud Hosseini, as this research is a collaborative effort with me. Okay, first of all, we talk about the motivation of the research, and then we discuss the mathematical formulations of the problem. After that, we describe the gradient enhanced methodology, and we explain numerical examples, the results, and the statistical analysis that we have done for this research. And at the end, we have the conclusions and the future research. Okay. Generally, modeling engineering and scientific problems using coupled partial differential equations or PDEs hold significant importance in the field of design. By incorporating coupled PDEs into our modeling and analysis, we can gain insight into the complex behavior and response of engineering systems. This approach allows us to account for the mutual influence and feedback between different physical quantities, and this leads to more accurate predictions and improved design outcomes. For instance, in the case of coupled thermoelasticity, the simultaneous consideration of thermal and mechanical effects is crucial for designing structures that can withstand thermal stresses and deformation. In this research, our focus is on coupled diffusion thermoelasticity. From an engineering perspective, one of the important problems in mass transfer problems involves the diffusion of mass within solid, such as the diffusion of gases within metals. Diffusion can be described as the random movement of a group of particles from areas of high concentration to areas with a low concentration. Fick's law in diffusion has a significant limitation in that it doesn't consider the interactions between substance and its medium. Several others have recognized this drawback and have explored non-Fickian diffusion and thermoelastic analysis. They have developed equations that govern thermal diffusion in an elastic body and have found that waves can propagate at finite speed. In the context of mass transfer, the coupling between thermoelastic fields and concentration of diffusive gases occurs when solid body is immersed in a gas environment. Various theories of generalized coupled thermoelasticity have been introduced in the literature, such as Low-Shulman, Green-Nappi, Day, and the others. But here, we base our study on the Low-Shulman theory of coupled thermoelasticity to investigate the transient behaviors of field variables, including mass, concentration, temperature, and displacement. In order to address the problems that are related to generalized diffusion thermoelasticity, there are different analytical and numerical methods, such as Laplace and Fourier transform, finite difference method, finite element method, and meshless methods like meshless spectroscopy. However, a major issue with conventional approaches is that they often struggle with the curves of dimensionality, and then we have additional spatial dimensions or complexity. These methods can become less efficient in terms of solution accuracy and computational time. So in recent years, artificial intelligence-based solution techniques, specifically deep learning-based approaches like PINN, have shown promise as effective and highly accurate methods for solving coupled PDE. So now we talk about our mathematical formulations. These are the governing equations for the coupled non-Fickian diffusion thermoelasticity. We are examining an isotropic thermoelastic strip that experiences thermal shock loadings as a result. These functions are defined in the spatio-temporal domain represented by variables x and t. The output variables are c as concentration, u as displacement, and t as the temperature. Non-dimensionalization is a crucial step in simplifying coupled equations. That helps us to balance contributions of variables during neural network training, and it can enhance the convergence. So we apply non-dimensional variables, and after that, we have the system of non-dimensional coupled P. So I believe most of the audience is familiar with the concept of PINN, but for those who do not have the background, we can say the general formulations of PDE as F for the differential operator. U is the solution to the problem, and beta is the boundary condition. So the loss term is fundamental component of a neural network. In conventional neural networks, we have labeled data to predict the values of the outcomes, predict the values of the output variables. But in PINN, the residuals of PDEs, initial conditions, boundary conditions, are utilized as the loss functions. Gradient enhanced PINN has already been successfully applied to several benchmark problems by you et al. In 2022. But here we extend this methodology to system of coupled PD. In a gradient enhanced PINN, we have an additional loss term, as you can see here. This term calculates the loss of the gradient of the case partial differential equation in a coupled system with respect to the J's dimension. Another important consideration in our research is that we do not have any data. So within the domain, there is no data, and so the loss term associated with the data is eliminated. Okay, here is the structure of the conventional PINN, except for the fact that we have 3 separate neural networks, each for an output. For example, for the displacement, we have a separate neural network for temperature and for the concentration. And these are aggregated, and we have the automatic differentiation that leads to the residuals of the PDEs. And after that, the optimization of the loss terms is initiated. Okay, for the numerical examples, in our research paper, we have investigated 3 different scenarios by considering various sets of boundary conditions. However, due to time constraints, I will only present one scenario along with a 2-dimensional example. To analyze the behavior of the system of PDEs, we have chosen copper as the material and determined the relevant parameters. The example involves a copper strip, as you can see here, that experiences thermal and mass concentration shock loadings on its inner boundary, and the initial conditions are homogeneous. This means that the strip is initially at rest. And to determine the architecture and hyperparameter settings for gradient enhanced PINN, we conducted multiple independent runs with various assumptions. Our research paper includes information on how the number of layers, given neurons, learning rate, number of epochs, and whether to use separate or unified neural networks impact the result. After analyzing the data, we found that the optimal combination of hyperparameters in terms of minimizing error is achieved by using 3 separate neural networks. Each consists of 5 hidden layers and 60 neurons, and the learning age is set to 1000, and the number of epochs is set to 50,000. For this scenario, we enforce the initial conditions for all 3 outputs and the boundary conditions for the thermal shock as hard constraint. This will ensure that they are fully satisfied. The trial solutions can be formulated as you can see in this slide. And the gradient enhanced PINN method is used to analyze the propagation of 3 field variables. Here we can see the distribution of non-dimensional mass concentration along the non-dimensional distance. These results are consistent with previous findings from studies that use the Laplace transform and Talbot technique. And here you can see the non-dimensional displacement along the non-dimensional distance for different points of time. And as you can see, the boundary conditions align well with the proposed methodology, and this confirms the effectiveness of gradient enhanced P. And here we have the non-dimensional temperature along the non-dimensional distance, and we have derived the behavior of the stress field, as you can see, for various points in time to gain a deeper insight into the propagation of the wavefront. These values align closely with the previous findings, providing evidence for the propagation of the wavefronts at finite speed and predictive capabilities of the gradient enhanced PIN method. And in order to expand our understanding, a series of analyses were performed to assess the influence of relaxation time on the wave propagation of non-dimensional mass concentration. These results further support the previous findings and demonstrate that reducing the relaxation time leads to a decrease in the speed of wave propagation in dimensionless mass concentration. And in order to investigate the impact of weights of PD gradients on the predictive capabilities of gradient enhanced PIN, we implemented different gradient enhanced PIN using various weight values and compared the results. The hyperparameters for all of these neural networks were set up similarly for all the implementations. I should note that in this case, 6 loss terms associated with PD gradients were assigned the same weight values, and the computational results for the dimensionless concentration, displacement, and the temperature are shown in these figures. As you can see, the final results are sensitive to the weights of PD gradients, and when these weights are set to 1,000, the results are satisfactory enough. As you saw in the previous slide, it was found that GB with a certain weight value achieves satisfactory results. To further justify the selection of this value, this weight, a non-parametric statistical analysis called a Friedman's test was conducted. These tests are statistical methods that do not rely on specific assumptions about the distributions of the data. So if the null hypothesis is rejected, we should do a post hoc test to identify the specific treatments with different distributions. The Nemeni test, also known as Wilcoxon-Nemeni-McDonald-Thompson test, is used. In this case, it compares the distributions of the 3 groups of results. These groups are the analytical method, gradient enhanced PIN with the rate of 1,000, and gradient enhanced PIN with the rate of 1,000. So the box plots of 2x2 comparisons prove that there is a significant difference between the distributions of the analytical solutions and gradient enhanced PIN with 1,000. On the other hand, the null hypothesis is satisfied for the distributions of the analytical results and gradient enhanced PIN with 1,000 for mass concentration, temperature, and displacement. As the second scenario, we applied the gradient enhanced PIN method to solve a 2-dimensional generalized thermoelastic diffusion problem. This problem involves a homogeneous and isotropic body experiencing thermal and chemical potential shock, as you can see. We do not present the formulation again, as they are practically the same as in the previous example, two variables known as x and y. And I should mention that the displacement in this problem is composed of two components. In this example, we consider a range from 0 to 3 for both spatial variables, x and y, as you saw in this figure. The distance of OA and OC are both equal to 3 and represent the non-dimensional measurements along x-axis and y-axis. And initial conditions are homogeneous, and the thermal shock and the chemical shock loadings are imposed as boundary conditions. We conducted comprehensive sensitivity analysis to fine-tune the hyperparameters of the neural networks. Based on the partial information that you can see in this slide, it suggests that using an architecture with 4 hidden layers, each containing 40 neurons, can result in reasonable accuracy after 80,000 iterations. The typical scenario C, as you can see, achieves the lowest magnitude of relative error except for the temperature, which is slightly higher compared to scenario B. The results shown in these figures indicate that the gradient enhanced P method can really can have the satisfactory results in comparison to hybrid Laplace transform finite element method. And this suggests that this approach is a viable option for solving problems in higher dimensions. And gradient enhanced beam enables the exploration of complex system behavior at different time points with a wide range of parameters. And for the conclusion, I should say that we consider 3 separate neural networks for the gradient enhanced P for the field variables, including concentration, displacement, and temperature. Some boundary conditions and initial conditions are enforced as hard constraints. Gradient enhanced P completely learned the transient behavior of field variables. The effect of relaxation time on the behavior of non-dimensional concentration is studied, and critical role of weights associated with loss of PD gradients in convergence and accuracy of the final results is determined. And we have gained reasonable accuracy in a 2-dimensional thermoelastic diffusion problem. For our research directions, we have several exciting avenues to explore. Firstly, one of the major challenges in the multi-neural networks is the fine-tuning of hyperparameters. To address this, we are considering the implementation of an intelligent approach to automatically tune these hyperparameters. This could involve incorporating heuristic or meta-heuristic algorithms or exploring methodologies like a response surface method. Next, we are intrigued by the potential of working with systems of capacities that involve differential terms of higher orders, such as 5 or 6. And another promising area of research, which we are currently working on it, involves tackling systems of stochastic coupled PDEs, particularly when the constitutive properties of materials have uncertainty. Traditional methods like Monte Carlo simulations can be both time-consuming and cumbersome. So we aim to develop a pin-based approach to streamline and enhance our ability to handle such complex systems. And furthermore, there are numerous unexplored research opportunities in the field of mechanical and industrial engineering, where pins can be effectively applied. As an example, we have recently used a modified structure of pin to analyze a problem of shock-induced Moore-Gibson-Thomson coupled thermoelasticity analysis in porous media. And we think that looking ahead, we are planning to delve into the world of metal materials with a specific focus on studying frequency of band structures in phononic crystals and metal materials. And thank you for your attention.
Thank you. Thank you for your presentation.
Thank you. You're welcome.
Do we have any questions from the audience? Or do you want to comment something?
Yeah, thank you very much, Katayoun, for taking the time.
Thank you.
You didn't show any comparisons with PIN. In all the cases that you've done, gPINN beats PIN?
Yes, we have compared the results with the PIN, but these are in our research paper, which is published in Engineering Applications of Artificial Intelligence.
Okay. Also, the system that you had, I think the highest derivative was third order, right? You had the third order derivative.
Yeah. Yes.
So when you take gPINN, you have fourth derivative to get the gradient. So isn't that expensive? Are you using JAX, or how do you compute these derivatives, the higher derivatives?
I use the TensorFlow as the platform for computing the derivatives, and I should mention that we compare the cost of computational time for the gradient enhanced PIN and PIN also, and it was twice the time of the computation.
Yeah. That's typical.
Yeah.
Great. Thank you.
Thank you very much.
I think JAX, we found that JAX can do a better job in terms of accuracy and also a cost for the higher derivatives. So JAX may be a good implementation for gPINN. There are some people in the audience who have experience with that.
Thank you for your suggestion.
Yes. If you can try with this JVP, and you gain like it's like 30% faster, so it's actually a lot.
Juan, can you identify yourself?
Yes. Hi. I'm Juan. I'm a PhD student working with Professor George. And yeah, JAX is faster. Yeah, you can try it, especially if you have like a lot of like higher dimensions. If you try the forward differentiation and you use this JVP that they have this in library, it's like I mentioned from 20 to 30% faster. It may be good to try.
Thank you for your suggestion.
Sure.
Excuse me, I have a small question. Can I ask? Okay. May I ask you what kind of data you use for validation the result as a reference value? Did you have the simulation data?
Please identify yourself so the speaker knows who you talk to.
Okay. My name is Albert Manavi. I'm a PhD student at Technical University of Munich, but at the moment I'm a guest researcher at George at Brown. And I wanted just to know, how did you validate the result of the gPINN?
Yes, we have utilized the data from the previous studies, as I mentioned earlier. These were from the Sherif and Saleh in 2005 and Hosseini et al. In 2016.
Okay, they exactly solve this non-Fickian.
But we do not use the simulation data. We use the experimental data that we have gained from this research.
Okay, thank you.
Hi, this is Yuxin from Crunch Group, and I'm a visiting scholar here. I have a short question. in page 15, it seems that the weight of the gradient have a strong effect on the results. So do you have any suggestions for the weights or for the gradients?
Yes, currently we are working on these heuristic and meta-heuristic algorithms to tune the parameters and embed them into the gradient enhanced pin or pin, gradient enhanced pin to automatically adjust the weight. We have done some
Sorry, is it me or the internet connection is not stable?
I think, I don't know if this is my internet connection.
No, I think it's because of internet in Iran, the poor connection in Iran. Yeah.
Yes, unfortunately, I'm very sorry. I did my best to have a stable connection, but
It's all right. It's all right.
Yeah. We understand your situation, Katayoun. Thank you for your.
Thank you. Thank you, Notre.
Thank you.
Is there any other question?
I thought I was listening to Nazanin because they have similar accents. Katayoun and Nazanin. Nazanin, identify yourself, so you say hi to Katayoun.
Hi, Katayoun. I cannot turn on my camera. I am a second year PhD student at Crunch group in biomedical department. Yeah.
Nice to meet you, and I'm really, it's really my pleasure to meet an Iranian girl who is studying Brown University.
Thank you.
It's an honor for me.
Thank you.
All right. If there's no more questions for our speaker, thank you for your presentation. And this comes to an end to this week's Chrome seminar. By the way, I think starting from next week, we're using a new link for Chrome seminar. So to check out the reminder email we send next Wednesday, I think. And yeah, everyone have a good weekend ahead. See you next week. Bye.
Yeah, thank you. Thank you, Zogren.
No problem, George.